Are you mic'd up? Okay, very good. So our next talk is going to be from Jairo, who's going to be talking about doing some stuff with MathComp. Thanks.
Yeah. Hi, everyone. So this is some work in progress on formalizing what we call a first-order differentiable logic. So first of all, like an introduction to what quantitative logics are that we will use to define differentiable logics. And I'm going to do it through a little example. And the idea is very simple. Like quantitative logic is just a logic that models some subset of the extended real numbers. So basically, you have a mapping that goes from formulas in the logic into some number in the real line. For example, in good old logic, you can interpret conjunction as a minimum. That's the basic idea of it. And then we say that a differentiable logic is thus a quantitative logic where the functions on the other side of the interpretation happen to be differentiable. These logics are useful for machine learning stuff. So just in case, like a little mouth opener about machine learning, the idea is that you have a loss function and you want to approximate the minimum or the maximum is equivalent of this thing. And this loss function includes as a parameter a neural network. And you have some data, inputs and outputs, that are assumed to come from an unknown function that here I represent with h, right? So you can think of this process, or as the neural network, as an universal approximator of some unknown function, which means it's not very trustworthy, right? Because it's an approximation process. We can try to make it more trustworthy through these differentiable logic stuff by imposing some extra constraints. So like the idea is that you are going to try to integrate symbolic knowledge into this fuzzy approximation process, and you can do that by modifying the loss function or modifying the architecture of the network through some formula in the differentiable logics. So you move into the real semantics, and because you're in the reals, you can integrate it into the optimization process. They also happen to be useful for giving programming support for this kind of process. For example, the vehicle language is useful for integrating this kind of symbolic knowledge into training. So you can write a specification in the logic, and vehicle is going to compile that into a loss function that you can use for training. So we would like to have guarantees about the performance and correctness of tools like vehicle. There is a problem, though. Like these logics, quantitative logics, can either come from the logic community or from the machine learning community. And the ones from the logic community are very nice from a proof theoretic perspective. So like they have these usual properties, completionality, residuation law that I'm going to talk about later, and have a calculus and all that stuff. But they are not very nice for optimization because they are not differentiable or are discontinuous or all these different things. So for example, you have substructural fuzzy logics. But if you move into the machine learning community, you get these quote-unquote logics that are good for optimization, but are not really logics. They don't have a calculus, they don't have semantics, nothing like that. So it's just a mapping between formulas and functions that happen experimentally to work for this kind of thing. What we want to do is to build a logic that is both things, good for optimization and has good proof theoretic properties. And we call that logic soft bunch logic. And we say that it's a well-behaved differentiable logic. So the idea of the logic is that we are going to pick some semantics by this guy called Matteo Capucci, which introduce a softness modality that will be useful for this kind of balance. We pick bunches from the logic of bunch implications and hypersequence from fuzzy logics. I'm going to talk a little bit about this later on. And of course, we want to guarantee that what we are doing is correct using MathComp, and that means also extending the library a little bit. So here's like a minimal example of the logic. It's inspired by linear logic. So you have both additives and multiplicatives, with the difference that the additives are going to be, maybe it's too tiny to see, but a little p that is going to be a rational number. Semantically, then this thing is, I hope you can see, but it's basically a p norm. So you have everything to the power of p, and then you add it up and wrap it in 1 over p. And this is nice because as p grows bigger, it approximates the maximum, which is known to be a lattice operation, just like the additives in linear logic. So like the idea is that you're going to use this p parameter to balance like behavior of the additives and continuity, right? Because the maximum is not continuous. Then you extend everything into the extended real numbers because you are going to interpret top as infinity and 0 as bottom. And multiplicatives are given by division and blah, blah, blah. So to do this, we will need to modify the power function in MathComp because it proved insufficient. I will talk about that later as well. So here is the structure of bunches and Hölder sequence. Just in case you're not familiar with bunches, basically the idea is that just like you had multiplicatives and additives in formulas, you will do the same at the level of context. So the comma is going to represent the multiplicatives, and the semicolon parameterized by p is going to represent the additives. Hypersequences are basically list of sequences, and we are going to interpret this bar basically as a disjunction. Just like the white space in a calculus is sort of a conjunction of sequences, we are going to interpret the bar as a disjunction of sequences. I don't give the full semantics of sequences and hypersequences, but this is like a mouth opener. We're going to interpret everything on the left side of the sequence as a conjunction and everything on the right side as a disjunction, either additive or multiplicative. And we say that a formula is valid if it's bigger or equal to 1, basically, which at the level of sequences means that the thing on the left is smaller than the thing on the right. So for example, we have this prelinearity formula that is known to be valid in the logic. Why we care about this? Because this is an important formula from the perspective of fuzzy logics. It's basically what makes something a fuzzy logic. And the problem is we can only prove this using hypersequences, and that's why we have them. We also have a calculus that is known to be sound, and we are currently working on extending that calculus to make it complete. Here's a little taste of the calculus. It's basically the calculus of bunch implications with these additional rules that are useful for moving around, playing around with the p. Basically, you can make the softness parameter bigger as you go up the proof. Ideally, we want to, when we are done with the propositional case, move into the first order case, which means we need semantics for quantifiers. And well, we had the semantics for disjunction were addition, like the p-mean, the p-norm for two elements. So we are going to generalize that into the infinite case, and the infinite case of an addition is sort of like an integral. So that's like the intuition as to why we picked this. But this is still just a p-norm. But here it will be specifically over a probability space because it gives us some extra properties that are nice for optimization and also to behave more like quantifiers. Similarly, this thing is also parameterized by a p. And as the disjunction case, as it grows bigger, it approximates the supremum. But also when it grows smaller, it approximates this thing, which is called a geometric mean. It's just like a characteristic of the logic. And we can define universal quantification as usual, as the dual. But for this, we will have to modify what validity means, right? Because now we have to deal with variables and all these things. An important lemma that will be useful for extending validity is that these semantics for quantifiers are monotonic, right? Like if it's monotonic increasing. But to prove this, we need to use Hölder's inequality, which is this thing. And unfortunately, in MathComp right now, this thing is only formalized for the reals. So we need to formalize it for the extended reals. So in terms of formalization, we are very much in the early stages. There is previous work that formalizes some propositional differentiable logics. We want to do the same for logic and then extend it into first order. And of course, MathComp already has a bunch of results, like probability spaces, like X integrals, and we want to leverage all these things. So currently, we're basically extending the library with extra lemmas and stuff. This is like the correct version of the power function, which is nice. And this is ORS, which is a lot of cases. But basically, you have to deal with an exponent that is an extended real number. So it could be infinity. And so you have to do a bunch of case analysis for it. This is like the 5th version of this power function. We are working with people from MathComp, and hopefully this is the one that will get approved to be integrated into the library. And in terms of Hölder, it's basically the same lemma that is already in MathComp, except that it's for the extended real numbers. That's it. Which means a bunch of case analysis. And that's it.
Questions?
I also have a picture of the entire calculus, just if anyone is curious.
So I'll start off with one. I remember the very first slide, you had all the great things about, you know, the logics that the...
This one?
Yeah, you had, oh, these are the great logical properties, and these are the other ones. So I assume that your system has all of these things, or a subset of these things, or
yeah. So, sorry, I forgot to explain this. Like, I don't have a formal definition in the presentation. The answer is hopefully yes. Okay. But we haven't formalized everything. So like we know it's continuous, we know it's monotonic, we know it's shadow lifting. We are not sure about this one yet.
Okay, okay. But it has...
It does have compositionality, resolution, prelinearity, and we are here. We know it's sound. We are trying to make it complete.
Approximately. Go towards affinity would be the same question. Any other questions? I guess I'll have one more. I was trying to get a sense of what these functions were doing. You had that neural network, right? You had a phi on one side and a phi on the other. So what are these exactly doing?
Right. So this varies from methodology, but imagine this is like a computational graph, like a circuit, where each of the nodes is an operator. So it will be like the semantics of conjunction and the semantics of whatever is connected to that, and so on. So basically, you add that at the beginning or at the end of the network and parameterize it over the inputs or something like that.
Any more questions? Well, if not, let's thank our speaker again.